In the past lectures we have learned a lot, but still not enough to give a full proof of this theorem. Don't be afraid, we're not going to learn the rest, but just trying to prove as much as we can and then believe the rest. So maybe call it a sketch of a proof. So for statement A, this direction of the proof is not interesting. We already know this from the good old Polski theorem, because that says that applicability implies stability with or without invertibility. So the only interesting direction here is this. And actually we have almost done that implication also in the old Polski theorem. Well, in the proof, I just copied the interesting piece in here. You will recognize it, hopefully, or you can check back. We showed that stability of our sequence AN implies injectivity of the operator A, and we concluded injectivity from this inequality here. Okay, and now take a second and look at that inequality, and you will recognize that this is nothing but the property we now call the operator is bounded from below. And now recall that boundedness from below is actually more than just injectivity. It's injectivity plus closeness of the image. And all that is missing for a proof of invertibility of A is injectivity of the adjoint A star. And this is where the additional condition comes in. You see, we need a statement about the adjoint, and that's why this is here. Okay, and the proof goes like that. From the stability of your sequence AN, you can easily conclude that also the sequence AN star is stable. And to see that, you just have to recall that the inverse of AN star is just the adjoint of AN inverse. So it always exists as soon as this inverse of AN exists. And also the norms are equal. Well, of course, you can just put norm bars to every operator in this equality and get that equality. And then you recall that the norm of the adjoint of an operator is equal to the norm of the operator itself. So you can drop that little star here. Okay, but stability of AN means that these are bounded, so consequently they are also bounded by the same bound. Okay, but now you repeat this argument here, but you apply it to AN star instead of AN this time. And this time the conclusion is that A star is bounded from below. How do we get there? Well, here you're using that AN goes strongly to A. So here you have to use our extra condition that AN star goes strongly to A star. This is where it's coming in. And then you get this. But now by lemma 8 from chapter 3, we can say that A is bounded from below if and only if A is injective and the image of A is closed. Okay, then same thing here. But now by lemma 7 in chapter 3, this, and this already guarantee the invertibility of A. Okay, well, in fact, we know quite a lot already. We can fully prove A. We're almost there. So we have seen that stability here implies invertibility of A. But now from the old Polski theorem, again, we know that stability and invertibility of A, if they come together, then they also imply applicability. So indeed, we even have a full proof of A. Should we talk about B? We're not going to get through B, but maybe we can talk about it. Yeah, come on, let's try B. For B, you need some techniques that we didn't see before, but I'm sure you understand. You start with the set of all bounded operator sequences. So this is like our little L infinity, but now the entries of my sequences are not real or complex numbers, they are operators. Something like this. Okay, so a point, an element of this set is a sequence of operators that is bounded. Now inside of this you study the subset of all strongly convergent operator sequences. So AN converges strongly to something, let's say A, and the other condition, also the sequence of the adjoints converges strongly, and the limit will be the adjoint of the other limit. And this is of course the set of all such sequences, not just one sequence. Okay, but that's exactly the setting where we are. So our sequence AN is one of these. And then you start to equip this blue set with operations. You can, for example, you can add two operator sequences by just adding them operator-wise. You can multiply a sequence by little alpha by multiplying every operator AN by little alpha, and you can multiply two sequences by, well, multiplying the operators in the sense of operator composition. So in that case, you will need operators from x to x, actually. And then you find that with respect to these operations, you have a null element and a unit element for multiplication. And then you can start talking about invertibility. So an element in blue, or a red element, which is a sequence of operators, is invertible if you find another element such that the two multiplied together give you this unit thing, which is just a sequence of unit identity operators. And then the next thing you show is that both the blue and the red set are so-called C-star algebras, which is of course clearly exceeding what we did so far. But the cool thing about C-star algebras is the following. If you have an element in your small subalgebra, the red one, that is invertible, then you know that the inverse is always automatically in your little red subalgebra. I mean, if it wasn't C-star algebras, the inverse could be outside, could be blue. But in fact, for C-star algebras, the inverse of an element in the subalgebra is again in the subalgebra. And the other cool thing is that the same holds true for more Penrose pseudo-inverses, and you can define also them in C-star algebras, and you would just get the sequence of the operator-wise pseudo-inverses. So the condition in B here, that our pseudo-inverses lead to a bounded sequence, means that the sequence of pseudo-inverses is in the blue algebra, but in fact, because we have the C-star algebra property, it's even in the red algebra. And this proves that the pseudo-inverses must converge to something, and their adjoints converge to something else. Let's call the limit of AN plus maybe B. Okay, and then you write down what it means to be a more Penrose pseudo-inverse. So let me just give you these two conditions here. You know that there are two more conditions saying that these products AN plus are self-adjoint, and also if you take them the other way around. Okay, and all you do now is just let n go to infinity, and then you know that your ANs converge to A, and your pseudo-inverses converge to B. And in the limit you will again have equality. But if you read that out, it says, well, together with the other two conditions that you can prove in the same style, that B is the pseudo-inverse of A. But on the other hand, B was the limit of AN plus, so indeed AN plus converges to A plus, and well, just without mentioning, we also proved that A has a more Penrose pseudo-inverse. So indeed, that's how you prove the difficult direction of B. The other direction is much simpler. Strong convergence by Banach-Steinhaus always implies boundedness. Okay, that's how you prove B, but you can see that we had to leave some gaps here, and we will not touch the proof of C. This is a lot more involved even.